All right, thank you very much. Thanks for the invite. So I'm Michele Ciampi. I'm a lecturer at the University of Edinburgh. I work mostly on cryptography and blockchain. And so today we are gonna see a tool that is very much used in the cryptographic world and also in the blockchain world. And so this is an extension of the talk you have heard on zero knowledge. In particular, zero knowledge Sigma protocols are a special kind of zero knowledge protocols. So Sigma protocol is an interactive protocol between two parties. We have a prover and a verifier. They share a common statement X, and the prover on top of this has a witness for the statement X. We will see a few examples later on, but at an abstract way, a Sigma protocol basically is shown on this picture where prover and verifiers exchange three messages in total. Okay, the prover speaks first, then the verifier sends C, which we will call challenge, and then the prover sends a last message, Z. So there are three main properties we want a Sigma protocol to enjoy. The first one is completeness. This means that when prover and verifier are honest, the verifier at the end of the proof will be satisfied, will be happy. In particular, this means that it will return 1 to say that he accepts the proof. Honest verified zero knowledge. This is similar to the notion you have seen in the previous lecture. So this notion says that there exists a simulator, there exists an algorithm, an efficient algorithm, that takes just a statement X as the input and returns a transcript A prime, C prime, Z, okay, that looks very much identical to a transcript that is instead generated by the interaction of a prover and a verifier, where actually the prover used the witness W. Okay, so what this tells you is basically that the transcript ACZ on the right actually does not leak information about the witness. So the witness is protected. Okay? So the witness is protected because I can actually generate a transcript that looks very similar. Okay, it's like identically distributed or computational indistinguishable from a real word transcript. And to generate this transcript, the simulator did not use any witness. Okay, so this tells you that this transcript does not leak the witness. Special soundness. So this is like soundness. So soundness means that assume that the prover is corrupted and you have a prover that wants to convince you about the validity of a statement that is not true. Okay, so X is not in L. So what you want from a protocol is that this prover should never be able to convince a verifier about the validity of the proof. So the verifier should never return 1 against such a prover. So special soundness is a bit different. It requires that if you have a transcript, okay, which is accepting for a statement X, and now let's say that you have another transcript which is accepting and it's for the same statement X. Moreover, it has the same first round, okay, the first message is the same. If you manage to obtain the second transcript with respect to another challenge, C different from C prime, okay, if you are in this situation and these two transcripts are accepting, there is actually an efficient way, an efficient procedure that can allow you to extract the witness for X. Okay, this is kind of like it expresses the fact that the transcript itself contains somehow the knowledge of the witness. It allows the extraction of the witness, and it means that the prover knew the witness itself. So let me show you an example of a Sigma protocol. So before doing that, let me introduce you to this hardness assumption. So the discrete logarithm assumption is based on this. So let's say you have a group. Okay, you have a group, and this group is of order Q, where Q is a prime. Moreover, this group has a generator. Okay, so I can generate all the elements of the group by doing G to the 1, G to the 2, g to the last, to the all elements contained in Z cube. Okay, I can generate every element of the group by doing this. So now the discrete logarithm problem states the following. It says basically that if I take a random value, okay, from Z cube, I do g to the y. So basically here I'm sampling a random element in the group, and I give the group description, the generator, and this value x to an adversary. As long as this adversary has limited computational power, by this I mean that the adversary is polynomially bounded in the security parameter in Q in this case. So basically, there is no way that the adversary can compute the discrete logarithm of x. So there is no way that the adversary can compute y prime equal to y. So now this means that, let's say that I want to convince someone about the fact that I know the discrete logarithm for this value x, okay? So there are many reasons why I may want to do that without disclosing y. And on top of that, like a verifier needs to be convinced about the fact that you know a discrete logarithm for the value x, because I mean you cannot just compute it yourself. Like the verifier cannot compute the discrete logarithm of x. Okay, if you could do that, there is no reason to engage in an interactive protocol. Like you know, if you have a statement for which you can compute efficiently the witness, you can just compute the witness yourself. There is no need of interactive proofs or of any type of sophisticated proof. Okay, so we are in the setting here where there is a prover. The prover knows the witness. In this case, is the discrete logarithm of x. The verifier wants to be convinced by the fact that the prover knows this witness. So the Sigma protocol works in this way. The prover picks a random element r, computes g to the r. So the first element, the first round of the Sigma protocol contains just a random group element. Then the verifier sends value c, which belongs to ZQ, and the prover terminates the protocol by sending z equal to r plus cy. The verifier accepts it. The verifier is happy about the proof if this equation holds, this equality holds. Okay. Now you can see this is very basic math that if the prover was honest, then this equality trivially holds. But the question now is like, why is this protocol like a good proof? Why would you be convinced that by verifying correctly this proof, the prover knows the witness, knows the discrete logarithm? Okay, and moreover, why does this transcript doesn't leak anything about y? Okay, so we just wanna communicate the fact that we know y and nothing about y itself. Okay, so to answer the first question, we want to prove that this protocol is special sound. Okay, so we will prove that this protocol is indeed the Sigma protocol. So to prove that something is a Sigma protocol, you need to prove completeness, special soundness, and honest verified zero knowledge. So the first property is completeness. That's, as I said, trivial to see. Special soundness. So let's assume that I have a transcript ACZ, and then I have another transcript that I have somehow. Like it's not important to see here how we can get this additional transcript. But let's say we do have this additional transcript, which is the purple one, that is accepting, with the difference that the first round is A, the second round is C prime, and the third round is Z. So those two transcripts are both accepting. So now what you need to show is that there is an efficient procedure that, given these two accepting transcripts, like it allows to extract y. And this is kind of easy to do, because let's look at what we have here. So z and z prime are computed as described it before. Okay, so the prover computes z equal to r plus the challenge times the witness. In particular, the first z value is equal to r plus cy, because c is the challenge of this black transcript here on the left. And then we have z prime, the purple z, which is equal to r plus c prime, because c prime is the challenge, times y. So now, if you look at these two equations, you will notice that we know Z because it's given by the protocol. Like we know Z prime, we know C, again, it's part of the transcript. We know C prime. So the only two things we don't know is R and Y. So what we have here is like we have two equations and two things we don't know. And so, as you know, it's very easy to find Y and R. In particular, we're interested in Y by solving this system of equation, and it's efficient to do that. Okay, it's efficient. It's polynomial in Q. So this gives you an intuition, an idea about the fact that to kind of generate this proof, you do need to know something. You do need to know why actually. Okay, but at the same time, we want to prove that the transcript does not leak anything about why. So this is done, as we said, by showing that there exists a simulator that only knows only knows the segment. Okay, so the simulator only knows X. So this may seem a bit contradictory, the fact that, okay, we want to make sure that if we receive an accepting proof, the prover knew the witness, but at the same time, here we show that there exists a mechanism to generate a transcript, which is accepting, and that is generated without the knowledge of the witness. So this seems a bit contradictory, but it's really not. And the reason is that the simulator has an advantage. And the advantage is that the simulator can decide all the elements of this transcript on its own. So the reason why the protocol, the Sigma protocols in general, and the Sigma protocol in particular, like it's hard to complete. It's hard to be completed by a prover that doesn't know why. Is because this prover here will send a first message A, and then upon fixing this first round, he needs to reply to a challenge that is given later on by the verifier. So what I'm saying here is that the order of the messages matter. If you can somehow arbitrarily decide in which order these messages are generated, then it's very easy to generate a transcript. And that's exactly what the simulator does. So the simulator will sample first a random challenge, a random second round, a random third round, and then it will compute A such that this equality holds, okay? Because this transcript needs to be accepting. That's the list we need to provide, okay? Now, if you look at how you compute A here, I mean, it's very simple. Like, if you now if you now multiply A by X to the power of C on the left and on the side, you get basically the accepting condition of the verifier. So this, we showed that we can create an accepting transcript without knowing the witness. Okay? Now, of course, observe that this simulator is just to prove that your transcript doesn't leak information about why. Like, you will never use this simulator in the real world. Like, in the real world, the protocol is executed as showed on the top. Okay, where it's very crucial that the message A is fixed, and then like the verifier can send a challenge C on which the prover then reacts with an additional message. Okay, this is what makes it non-trivial to generate a transcript for the Sigma protocol. Okay, so I'm going to show you another example. So, and this example, so before doing that, let me discuss another hardness assumption. Both these hardness assumptions are used a lot in many cryptographic applications. And that's why it's also important to have Sigma protocols related to these hardness assumptions. So first of all, let me say what is a Diffie-Hellman tuple. This is like, it's very similar to this discrete log assumption, with the difference that we consider Diffie-Hellman tuple where you have the group generator, you have some random element in the group H, and then you have two additional elements. You have U and V. So we say that the tuple is Diffie-Hellman if the discrete logarithm of U and V is the same. That's it. Okay, that's what you need to remember. It's not a Diffie-Hellman tuple if the discrete logarithm of U and V is different. That's it. Okay. So the hardness assumption says that an adversary cannot understand whether a tuple is Diffie-Hellman or not. Okay. So this is like not about the adversary not being able to compute something. This is about the adversary not being able to distinguish whether two elements have the same exponent, have the same discrete logarithm. Okay. And the Sigma protocol to prove that a tuple has this property is very similar to the one we have just seen. And the reason is that here, what I want to do is that I want to prove the knowledge of the discrete logarithm of an element. And I want to prove that the same discrete logarithm, I want to prove that there is another element which has exactly the same discrete logarithm. So the intuition here is that I can kind of run the same proof almost in parallel. Okay? So the only difference is that the protocol here on the left is basically the discrete logarithm protocol you have seen before, the Schnorr protocol. That's how it's called. Okay, and then I will run the first protocol using as a base G because I want the discrete logarithm of the element U in base G. That's what I wanna prove, that I know that this element. And now we will run in parallel another protocol, another sub-execution of the protocol, where the only difference is the base. Because if you look at the element of V, it has the same discrete logarithm of U. The only difference is the base. It's not G, it's H. Okay? So it's really more or less like running in parallel two protocols, two Schnorr protocol, where the only difference is the base I use. Okay? And the condition that the verifier will check, it's very similar to the previous condition. It's just that now you need to check that this condition holds for the left execution, let's say, and the right execution. Okay. What is very crucial, what is important here is that what guarantees that the two elements have the same discrete logarithm is that the prover will send only one Z value. Okay. So Z value here incorporates what? Incorporates R, which is a random element, plus C times Y. Okay. So Y is the same discrete logarithm, and the fact that you send only exactly one Z value and that you use the same Z value to check that the two equalities on the right hold guarantees you not only that the prover knows the discrete logarithm of both U and V, but that this value is the same. So to prove that honest verified zero knowledge holds, it's basically the same as before. You can leverage on the fact that you can pick C and Z, and then you compute A accordingly. And special soundness also, like what you get is that you just need to solve a system of equation and you can easily compute the weakness. Okay, so now Sigma protocols are very interesting because they are versatile. So what you can do is that if you have two Sigma protocols for two different languages, for example, Sigma 0 is the Sigma protocol to prove that two graphs are isomorphic, and Sigma 1 is to prove that the knowledge of the discrete logarithm, you can create a new protocol, which is a protocol for the OR composition, which means that basically I can design a new protocol that allows a prover to prove that either x0 holds is a true statement or x1 holds is a true statement, okay? And it's a compiler. So the way the protocol works, the way the compiler works is as follows. So let's assume that the prover knows only the witness W0. So the prover now will compute the first round of the Sigma protocol Sigma 0 using the witness W0 because that's what he knows. And it will compute, it will run the simulator of Sigma 1 using the statement x1. I mean, it doesn't know W1, so it can only execute the simulator. And it will send these two first rounds, A0 and A1, to the prover. The prover now sends a challenge and gives the freedom to the verifier to pick two challenges. Okay, the challenge C0 used to complete the execution for the Sigma protocol Sigma 0, and the challenge C1 to complete the execution for the Sigma protocol Sigma 1. Okay, and the condition is that C0 XOR Sigma 1, C0 XOR C1 must be equal to C. And the prover can easily compute to accepting transcripts because, I mean, one accepting transcript is this purple transcript, okay? And so to compute the challenge C0, the prover will compute C XOR C1. C1 is fixed. he will get C0. C0 can be now, will be a random value, basically. If C is a random value, C0 will be a random value. But the prover knows how to answer to a random challenge for sigma 0 because the prover knows the witness W0. And so he will be able to generate also this black transcript related to sigma 0. Okay. So that's how it works. Okay. You do the opposite as in the case where the prover knew the witness W1. Okay. So it's like one transcript will be simulated and the other transcript will be honest. So you can prove that this type of composition of two sigma protocols yields to a new sigma protocol. So this is still a sigma protocol. In particular, you can easily prove that it enjoys special soundness. It's easy to show that. I'll give you the slide later, so you can give a look that this actually works fine, and it's honest verified zero knowledge. You can also compose in N, so you can design a sigma protocol where you prove that you know both the witness for x0 and the witness for x1, or more simple. So this is much more simple. And this is something you can easily come up with, because if I want to prove that x0 is true and x1 is true, here it's really trivial because I know both witnesses, so I can just run two sigma protocols in parallel, and that's it. Okay, there is nothing tricky to do here. Okay? The only thing you need to be careful is that the challenge you use must be the same for both protocols. So I kind of lied a bit when I said you just run them in parallel. It's not true, because the challenge must be the same. And this is crucial because when you want to prove special soundness, you want that if I get an additional transcript for a new challenge C prime, I should be able to extract both witnesses for x0 and x1. Okay. So when I get a new challenge, the fact that the two sigma protocols share the same challenge means that when C prime differ from C, I can invoke the special soundness of both sigma protocols and extract both W0 and W1. Okay, so that's very important. Okay, so I'm going to show you the last nice application. There are many others, but let me show you one simple and interesting application of sigma protocols. So with sigma protocols, you can construct commitments. Okay, just a brief recap. So a commitment scheme has two algorithms. There is the green algorithm that is the commitment algorithm that takes the message and generates a commitment, this bold com, and some decommitment information. When you want to open the commitment, you can execute this decommitment algorithm that takes the commitment, the message, the decommitment information, and returns 0 or 1 depending on whether the opening was valid. So what we want is that a commitment is hiding, which means that if an adversary receives only com, this bold com, he doesn't learn anything about the message, and it must be binding in the sense that once that I send a commitment, I can open this commitment only to one message. So with Sigma protocols, you can design a similar type of commitments, but those are instance dependent. So in particular, all the algorithms now are parameterized by an NP statement. And what you have is that hiding holds only when X is in L, and binding holds only when X is not in L, so when the statement is false. And the construction is very simple here. So the way the commitment algorithm works is that it takes as input the statement, it takes as input the message you want to commit to, and generates an accepting transcript with respect to this statement and with respect to that message, to the message M. So your commitment now is basically A, the first round of the Sigma protocol. To decommit, you just run the algorithm of the verifier, and you check that com, M, and dec, which is basically A, challenge, C, and Z, that's how we were calling those guys before, is an accepting transcript. Okay? And now you can see that binding in this case holds because if you manage to open the same commitment in two ways, it means that you have a verifier that verified correctly with respect to the message M and to M1. But this means that the verifier here is like two accepting transcripts for the Sigma protocol that share the same first round, which is this bold com, with respect to the two different challenges. And this means that there is an extractor that can extract a witness. And this is a contradiction because we said that X is not in L. Okay, so binding holds. So hiding holds intuitively because the fact that the Sigma protocols have a simulator means that the first round of a Sigma protocol actually does not leak, does not contain any information about the challenge. Okay, so that's why this Sigma protocol is also hiding. So to conclude, so you've seen some applications of this of like these Sigma protocols in the sense on how you can combine them to obtain more complex protocols. But Sigma protocols are like very important. Like they are the base for like constructing efficient non-interactive proofs. So once you have a nice Sigma protocol, it's very easy to like turn a Sigma protocol in a non-interactive proof. And they lead to practical extractions. And they're used a lot in the case where you want to design an identification scheme, where you want to identify to someone, and you also don't want to show actually, you want to just prove that you have the right to access a service, but you don't want to disclose what your identity really is. Okay, Sigma protocol gives you this feature where you can prove that by proving that you know some secret, but not disclosing what secret, you can identify yourself to a service without disclosing who you really are, which is a very important property. And you can design Sigma protocol for every NP language. These Sigma protocols can be more or less efficient. So efficiency really depends on the type of language, but in principle, every NP language has a Sigma protocol. Okay? And so that concludes this small lecture. I'm happy to take questions now.